We're going to talk about SRv6. This is segment routing over IPv6 for simple, scalable, and seamless layer 3 overlays. And then after I go over that, my colleague Adi is going to talk a little bit about automating this solution. So for those not familiar with segment routing, it's a network paradigm with functions encoded in the data plane packets. Whether it's MPLS or IPv6, the information about these segment IDs is transmitted over the network using existing control plane protocols like BGP or your IGP, in particular for this demo, ISIS. And with MPLS, it's reusing the existing label field to represent the segment ID. And with SRv6, it's using the existing IPv6 destination address field to represent segment ID. In addition to that, with MPLS, with the concept of a label stack, with SRv6, there's the concept of an SRh or routing header that contains the other segment IDs that are in the packet to be processed in order. Now, the use cases for this abound, but one that you could think of is network segmentation for, say, a cell site router that needs to provide different service contexts. It could be a layer 3 VPN for a large backbone provider. It could be a large enterprise network that's providing some sort of segmentation for guests versus employees. But anything you can use a layer 3 VPN for, you can use this for. And in addition to that, SRv6 has a lot of other use cases that are not even related to VPN by virtue of it being a network instruction. So with Arrcus, our operating system that runs on merchant silicon hardware, you can do both SR-MPLS and SRv6 L3 VPNs. This is shipping. You can do topology independent loop-free alternate or TI-LFA, including microloop avoidance with SRv6. And this is an optimization in the IGP to make a more resilient solution. And it's simple because you're advertising SIDs in existing protocols. You don't require LDP. If that's existing, you can throw it out. ISIS advertises what are known as prefix and adjacency SIDs, and these are two types of behaviors that I might go into a little bit later. And BGP, which is the focus for this demo, sends the VPN encapsulation SIDs, which are NDT4 and NDT6, and I'll talk about that in detail later. The solution is also scalable because there's no switched path state in the core. There are no label switched paths. And the convergence time is determined by one optimized protocol, in this case ISIS, with no need to synchronize or coordinate two or more protocols. It's also seamless because it works over any IPv6 network. SRv6 packets are IPv6 packets. They have an additional header, but anything that doesn't understand SRv6, it's transparent. And because we use BGP for advertising VPN routes, it uses the same infrastructure that you would have for BGP in your network. So it's very seamless from a deployment standpoint. The demo topology that I'm going to show has a number of Arrcus routers. These are all Broadcom Jericho 2 based from a combination of Quanta and EdgeCore. We also support SRv6, L3 VPNs, and the other functionality on Qumran 2C or Q2C from Broadcom. You can see that there are three PEs, PE 1, 2, and 3. PE 1 and 2 on the left provide a dual homing solution to the customer edge router CE1 on the left. And PE3 on the right provides a single home connection to an Ixia that's acting as a second CE. You'll also notice that P1 and P2 are IPv6 only nodes that are just transiting IPv6 packets for SRv6. And you can see here as well that we're sending bidirectional in these VPNs, V4 and V6 traffic that is carried over this core with an IPv6 header with an SRH in most cases to bring it to the correct VRF and correct table on the egress. You can see the AS numbers as well. That might be useful for reference as we go through the demo. So one more slide before I go into the demo. I mentioned that a segment ID is a sort of network instruction, and you can think of it in that way, in that a packet that's sent to a SID that has a function associated with it determines what behavior is applied. It's not a tunnel per se, but it's a egress behavior that is dictated by the segment ID on the packet. So for example, if a packet arrives at the SID cafe 1100:2::, That is an NDT4 behavior. You can see that in the function column, and you can see that it's going into the network instance CEVRF1 and to the table, the v4 table there, which has this table ID. So autonomically, when the packet is received, it will decapsulate and remove the outer IPv6 header. It will use the correct VRFN table to look up the destination address of the inner packet and then forward it in that VRF as though it had been in that VRF from the beginning. There are other n.dt SIDs that can encapsulate and do lookup and forwarding behaviors in different VRFs, different tables. And there are also other modes for these that determine where segments are popped, whether there's, in the future, a layer 2 lookup or something along those lines. So you can see the flow chart. If the received packet is destined to one of my SIDs, then I apply a SID behavior. The SID itself determines what that behavior is. If there's no SID, local SID in the packet, in the destination of the packet, then it's just a transit packet. It will forward it as usual for IPv6 forwarding. So for the Ixia portion of this, you can see how this lines up with the topology shown in our slides. We have a site on the left, which has a CE in it. In this case, we're using the Ixia just to put some networks and some routes into that CE and traffic. And then on the right, we have an Ixia that's working as a standalone CE. So it's also running BGP with PE3. And we can see both BGP and BGP over IPv6 sessions configured here. So let's get into the CLI. This is the exciting part here. Let me close. Right. So I'm going to be switching back and forth because I just have one monitor set up here, but I wanted to show what this looks like on the PE1. So we are currently looking at PE1. This is the top left node here. And we're going to use a command to look at all of the routes in the RIB for CEVRF1. This is the VRF that's facing CE1. We can see that we have a combination of directly connected. Some of these are loopbacks. Some of these are the adjacency, the interface itself to CE1, and the rest are BGP. Some of these are coming from the other PEs in the network that are importing the same route targets, and others are loopbacks for that VRF on other PEs. Now, if we want to look at the BGP sessions in the default VRF, these are going to be the sessions that carry the VPN prefixes. So PE1 has connections to the two P routers. P1 is :10 and P2 is :20. You can see that these BGP sessions, iBGP sessions, are both established with L3 VPN address families being communicated. And then we can see on the other side, facing the CE, that we have two eBGP sessions facing CE1. One of them is for v4 and one of them is for v6. Now, we talked about segment IDs and how these look in the router are determined by the routing protocol clients that are using the segment routing. There is what's called a locator in segment routing. With SRv6, the locator is a v6 prefix. We look at the locator. We can see that it's configured as a /48. And this is out of a block of /32 that all of the routers in the network that are participating use. So if you look at the same command on PE2, you can see that it has Cafe 1000 and then 200 instead of 100. And then PE3, we can see that it has Cafe 1300. So these are all unique /48s. And out of this prefix, out of this block, the SID manager on the router will allocate SIDs for BGP and ISIS and other protocols. And we can see that if we look at the SRv6 local SIDs, that there is a client of a BGP in this case that's allocated two /64s out of that /48. One of them is a DT4, which says decapsulate and look up in the v4 table, and the DT6 decapsulate and look up in the v6 table. And again, these are both for that VRF, CEVRF1. And then there are also end and endx SIDs, which are associated with ISIS generally. You can think of these as sort of like the loopback or the prefix for this node. If a packet is sent to that address, it will go there first, and then there'll be a table lookup. If it's an endx, it's a cross connect after that happens, which will send it out a specific interface, in this case, SWP1 or SWP2. So you can use it for traffic engineering. But what we're going to be focusing on for this demo are the BGP SIDs NDT4 and NDT6. And you can see this on all of these PEs. They all have, out of their unique locator, a combination of NDT4 and NDT6 SIDs allocated that are also advertised with the prefixes in those VRFs, or in those VPNs. So once a router receives information in the VRF about a prefix, in this case, we're going to be looking at 2001 10.9999/64. This is a route that's coming in from CE1 on the left. So CE1 has a subnet on the Ixia. If we look at it here, there's a subnet 10.99.99, actually the v6 side. 2001 10.99.99 : and then it has 100 through 109. So we can see that in our sort of summary advertisement from that CE. This is then exported into the default VRF as an L3 VPN v6 route that will be advertised with a next hop and a service SID. Now you'll notice that the service SID is associated with a locator for PE1. So when PE1 advertises this route to the core and it's received by PE2 and PE3, we can look at that here. So PE3. One moment. We can see that it's received the same route from PE1, and it has these attributes, these special attributes that define the endpoint behavior and the service SID, along with the next hop that tell it what SID to use. In this case, if you recall, this 1100::3 or :3 is the NDT6 SID on PE1. So now PE3 knows how to send a packet over the VPN to get to PE1 and to get into the specific VRF and the specific v6 table in that VRF to reach this prefix on CE1. So we can do a VRF ping to verify this connectivity. And I will also do a Ixia traffic demo. So what we're doing now is pinging between the VRF1 on PE1 on the left toward a prefix that's in the VRF that's importing that on the right on PE3. And we are getting packets responded to. Now what you don't see in this ping is that in the middle of the network, there's an SRh being added, and it's using SRv6 to get to PE3. But if you capture this using something like TCP dump, which is available on our systems, you can see that these requests and replies look like this. So the echo request is represented with an IPv6 header first, and then an IPv4. The IPv4, these are the IPs that we used in the ping command. The destination is 192.168.13.1, and the source is 11.1. But SRv6 has added a v6 header on top of this, where the destination is the SID. It's cafe 1000:300:2:, which is on PE3 on the right. We can see that there's an SRh that has this single address in it. And what the router will do is it will receive this, decapsulate, look it up, realize this is a loopback in CEVRF1, and then it's going to do a reply. Now the reply needs to go back to that loopback that's in VRF1 on PE1 on the left. And in order to do that, it knows that it needs to add a SID as well in the reverse direction. In this case, it's the SID on PE1, cafe 1000:100:2. And so that rounds out the sort of the round trip path that's taken by ping Again, this is from PE1 inside the VRF to PE3 inside the VRF. And this applies as well if the CE were pinging a prefix on another CE. So let me cover the traffic now. Again, the Ixia setup has a left and right port. One side is advertising some subnets into, well, it's not advertising, it has some subnets, and they're being distributed into the CE BGP here. On the right side, it's running BGP and it's advertising a number of routes out of pools configured here. So we have a range of 20 addresses starting at 200.1 for v4 and a range of 20 addresses starting at 3,000, et cetera here. We can see these as well if we run the show command. For instance, so we can see all of these 200.1 prefixes for v4 and the SID that's associated with those, how to reach it. And then for v6, we can see the 3000 colon prefixes that are, again, these are being advertised by the Ixia. And then it's basically packaging these with a service SID for the core for L3 VPN with the correct SID and DT6 to be able to reach it, decapsulate it, and get to it. So now on the Ixia, we have traffic set up that's running between these two ports. We can see that there's no loss. This has been running for almost 23 minutes. So that kind of verifies it. Now, with SRv6, you might see that, okay. You might want to troubleshoot. For instance, you might want to know if a BGP route or advertisement has come in from your route reflector or from a remote PE, and it's telling you that to reach this VPN prefix that you need to use this SID. You might want to, in more complex situations, know what SID list is going to be added to this packet if there were multiple SIDs, and you could do that with this tunnel command. You can look as well at your local SIDs and see what are going to be advertised on your own routes that are going out, depending on which VRF they were received in or which VRF they've been exported from to the default VRF. If you're doing anything with ISIS for segment routing, and this is a little bit different topic than what we're doing with BGP. You can see here that in ISIS, in the TLVs and the LSPs that are being received, that there are a combination of end and endx SIDs. The endx SIDs allow you to send a packet to a core node and have it go out of a specific interface on that core node. So this is useful for traffic engineering, for example. You can see here that P1, you can just sort of almost like a menu. If you want to send a packet that goes to P1 and then goes out the interface toward P2, you just put the SID listed here on the packet. This might be something that's communicated with BGP link state to a controller. That controller might create an SR policy that is injected back into the head end based on some business logic or some rules or coloring that's required for the treatment of that traffic. These SIDs are also used for TILFA and microloop avoidance to guarantee that a packet going on a protected path won't be looped back to the destination and won't experience microloops along the way when there's a topology change, although we're not demoing that here. So one more thing I wanted to show is our analytics platform.
Quick question on that.
Yeah, please go ahead.
So on the SID side, can you also use that for NFV? So you can do an NFV insertion if you wanted to by basically pointing it to that specific SID. You could have an NFV function that you drop into and then pop back out.
Yeah, possibly. If you have a server connected on that interface or in a specific interface that you want to receive those NFV routed packets, that could be done as well. Yeah. One of the great things about SRv6 is that it works over IPv6, so you don't have to have ubiquitous end-to-end deployment of the SRv6 capability. If you have it in enough places that the NCAP, DCAP, and any sort of TE logic is done at the nodes that support it, then it'll work, even if you don't have it ubiquitously deployed.
Right. So you could just have a v6 endpoint. It doesn't even know the difference because it doesn't know that you're running SRv6. It doesn't need to know about that portion at all, right? It just needs to run.
Yeah. As long as your VNF for your function chain downstream of that knows what to do with the SRv6, then you're good.
Right.
Yep.
Yeah. Okay.
Yep.
Path computation element kind of controllers is supported by Arrcus.
Yeah, so we don't have a PCE at this time. However, with the ability to integrate with some of our netconf and automation packages, which Adi will talk about, some of the integration options are there. If you're looking specifically for BGP link state or using BGP to communicate SR policies or PSEP, I believe that's all roadmap for us at this point. But again, the integration options are there if you have the flexibility to work with one of the interfaces that we have now.
One of the key things I also want to add, Carl, there is that there's standards interfaces. The APIs are standards. It's OpenConfig, netconf based, OpenConfig based models over netconf, and so essentially existing controllers that support PSEP can essentially have an easy plugin as well, in addition to the workflow stuff that Adi is going to show.
Great, thanks, guys.
That's the beauty of this approach, is that it scales very easily across any kind of environment. We don't make a religious requirement about requiring our own controllers or our own set of solutions.
Yeah, thanks, Murli. So just one more thing before I hand it over to Adi. So we have a platform known as ArcIQ. Now, ArcIQ is an analytics and deep insight platform. This has a web interface that allows you to look at telemetry information that's come from your network. We stream JSON over Kafka for most of this data, although we are also able to do telemetry streams for BGP, using BGP, and we have other information as well, like SFlow, and we're adding to this over time. For segment routing for SRv6, one of the useful things that this can do is show you some of the CLI information that I was looking at as far as SIDs go in an easier to access format potentially. So the 5 routers in the topology, 3 PEs and 2 P routers, are all currently streaming telemetry to ArcIQ. And if we want to look at the information for, say, PE1, we have all the platform information here, all the information about software version, hardware, system information. And in the segment routing IPv6 dashboard, we can also see what locator is configured. And this is that CAFE 1100/48, as well as some fields known as locator node and function length, which apply to what range of this address is used for SRv6 function and arguments. And then the local segment IDs that have been allocated by our SID manager. And you can see here again the NDT4, DT6 for VRF1 and VRF2, as well as the ISIS or IGP associated SIDs and index. In addition to that, we have paths for NDX that show which interface will be taken for that NDX SID.
Hey, Matt, this is Jeremy. I got a quick question for you. Is ArcIQ also a service provisioning product, or is it exclusively?
ArcIQ is primarily visibility. And so for the most part, it's a read-only approach. We have other information, like you can look at the discovered topology from the IGP and sort of visualize this. All this, again, is not pre-populated. This all comes from real-time telemetry. We have LLDP topology and BGP topology as well. And again, you can see here that we have prefix looking glasses that can look at all these prefixes in the network and show the attributes, next hops. Security includes ROV, origin validation. But to answer your question, yeah, it's primarily visibility.
So if I'm presuming Arrcus and this, this kind of technology is geared towards service providers for the most part.
Not exclusively, but that's the focus of this demo, I would say. Yeah.
Yeah, I mean, so it seems to me, and I'm not a service provider guy, but I used to sell to them, that the service provisioning and service monitoring kind of go hand in glove. So I'm kind of curious what, when your customers ask about how do we provision these services and roll them out across a network, what answer do you give them?
Yeah, well, I mean, the typical answer is it's an integration exercise with your automation systems. And in the case of a lot of our cloud service provider, hyperscaler customers, they have their own preferred way to automate, their own preferred, whether they're using Ansible and templating that way, or whether they're using netconf natively, or if they're doing Python, we have something called ArcAPI that allows them to interface with our config and our operational state in a programmatic way there. As far as ArcIQ being a provisioning tool, I agree, usually they are hand in hand, but we have decided to focus on deep insight and visibility to help customers find issues, find problems, rather than accelerate provisioning and accelerate config management, which are definitely hard problems worthy of solving, but it's not what we're solving with ArcIQ at this moment. And Murli, if you wanted to add anything on that.
Yeah, no, I think you nailed all the points there. But Jeremy, I think the key point we wanted to mention is that most of our customers actually have reiterating the point that Matt made, have either existing proprietary service provisioning environments already baked in. They ask for open standard programmatic APIs, or they have workflow software automation systems like the stuff that Matt mentioned. So Ansible, of course, is very popular, and Terraform in many environments as well. And so, yeah, our approach has been that providing deep visibility and analytics brings a differentiated value to how they operate their environments day 2, day 3. That's one of the biggest gaps in infrastructure, especially in the edge and backbone, which is where a lot of these use cases are going to be deployed. And so that's where we wanted to focus first. Conceptually, sorry.
I'm sorry.
I was just going to say, conceptually, clearly, ArcIQ could be extended to add provisioning support as well. In fact, there was a lot of discussion internally as well at the initial days before when ArcIQ was launched, like a couple of years ago. But we decided to double down on visibility and insights, because that's what the big problem is right now for operations teams.
How would you characterize your market segment? I mean, is it mostly service providers or your customers that have this technology in production? How would you kind of describe your market?
Yeah, that's the unfortunately my presentation will cover that, and that kind of got disconnected. But fundamentally, our pitch, our approach has also been that the traditional silos, as I was just saying at the start of my presentation earlier, was that the traditional notion of silos, where you had a data center networking solution, you have a backbone solution, or you have a campus solution, those are completely being obliterated, because in fact, edge, the compute is moving closer and closer to the edge. So essentially, merchant silicon combined with with how edge is kind of emerging has made software solutions span across all of these environments. So that's why, if I could take a few more minutes, Matt, essentially, when we right from the day we launched, we have said that software-powered network transformation has a few key tenets. One is routing. It's going to be routing centric, whether it's in the data center top of rack or whether it's in the backbone and the edge. The other thing is we have built a very strong data path adaptation layer, what we call DPAL, or an abstraction layer in common parlance, that essentially allows us to port to any kind of switch, router, and even smart server environments. So that's why we announced the XGS-based switching family, Trident 3, Tomahawk 3, all of that generation. But at the same time, we have support for Jericho 2, which is what this demo shows, Qumran 2C, which is the edge-centric solution. So our customer base spans all of these. In fact, we have customer bases across all of these environments, as well as the transformative enterprise environments, plus CSPs, service providers as well. I don't know if that answered your question, but I wanted to give the context of why we have customers across the board. In fact, that is the key differentiator.
I understand the why. I think that why is almost table stakes. In today's world, everybody says, this is our operating system. It has a great API. It's one operating system across all of our devices. And that's our differentiator. And I'm trying to understand how Arrcus differentiates, in that table stakes kind of dialogue, because, I'm kind of an operating system nerd. I'm a network automation nerd. I love these technologies, but I'm trying to rationalize why somebody would choose to use Arrcus, versus some other, network operating system, whether it's from a traditional vendor or whether it's Sonic. What is special about Arrcus that makes somebody say, I got to buy that versus something else?
First principles based approach to building software. The traditional incumbents have had a 30-year run building, as I mentioned earlier, software that essentially built software bloat, one on top of the other, built software that is very, very siloed, very, very pin specific, place and network specific. Although you said that everybody says table stakes, even the legacy incumbents today have different OSs for different parts of their network. I mean, I know I worked in those environments. Most of us have worked in those environments. Essentially, you had a different operating system, different models, building the underneath of those operating systems. So it's never been the case that there is a common software. Then the other end of the spectrum for the incumbents, for the other end of the spectrum, essentially you have these, you've had startups. We're not the first that has talked about networking software, but what has happened is the prior efforts involved open source software, primarily Quagga FRR, and other variants of that. You kind of glue it together and say, hey, I'm going to use this for a data center. And that's why those solutions were very, very data center specific. What we're saying is that our network software, not that it's just deployable on any device, we're saying that it can be deployed in any kind of environment, whether that's a switching data center environment, whether that's in the backbone as a router, or whether that's at the edge, supporting 5G use cases. In fact, the demo that Matt is showing today is primarily a 5G edge access use case, where essentially you're simplifying all of the complex MPLS layers that you have, LDP, RSVP, underneath MPLS transport, removing all of those and just having plain simple SR. So what we're saying is networking it's not just about a device A and device B. Networking no longer should and is recognizing the different OSs for different parts of the network, whether a data center X OS or a backbone Y OS. That's the big point from the same vendor.
Yeah.
So that is the big.
Well, Murli, and related to that, the boundaries in a network and the roles that are defined. For instance, in the past, you would have a PE that would be 3 letters, 4 numbers from the vendor, and then you'd have a P that is probably not the same thing because they don't position it there, where you're buying a different silicon system, a different form factor, a whole different product line for your core. We don't have that distinction in a lot of ways, and because of that flexibility, if you wanted to deploy the core with Arrcus J2, you could, and then in the future you wanted to turn it into a PE and make it an edge location or put servers, compute, customers there, you could very easily do that, both from a feature functionality, hardware capability, but also from a protocol simplicity standpoint, that we're not creating these sort of artificial boundaries between what's edge, what's core. So this kind of ubiquity was something that we really gravitated to with SRv6 and with segment routing in general. Beyond the fact that it's clearly the next gen approach for delivering these types of network services. And I think that that's a big differentiator as well if you compare us with some others in the marketplace.
So I think what you're saying, I mean, I'm kind of translating what you're saying, but I think what you're saying is if I'm the kind of company that wants to deploy SRv6 because of the reasons of what we're trying to achieve, then Arrcus is a really great choice for, the reasons you've described. But for general purpose networking, like, in the network that I manage, parts of it are that look and feel like a service provider. Many parts of it look like a data center. Many parts of it look like a campus. They have aspects of power over Ethernet. The whole 9 yards. Like we do all of it. And we've used operating systems that kind of touch the boxes that live at every part of the network, but we don't use SRv6, for whatever reason. So is Arrcus's kind of differentiator the fact that it does SRv6 better than anybody else, and it's easier to manage and easier to roll out and troubleshoot?
There are two aspects to that. Just real quick.
Go ahead, Matt.
Yeah, I was just going to say that the first aspect of that is what's the differentiator in terms of being able to cover enterprise, switching closet, PoE, data center, IP clo, et cetera. We cover all of that. We have platforms that are geared towards Tor and 1 gig E. We have platforms that are geared toward 100 gig E, future 400 gig E data center spine. We have XGS and DNX if you're into the Broadcom chip nomenclature. What you're seeing today is just a portion of our portfolio, and there's a lot of other stuff that's not being presented. The second part of that was what's the differentiator specifically for SRv6. And I think that the takeaway you can have here is that we can do it on merchant silicon as an ODM built box that can, at the price points that you get with that approach, do very, very feature rich SRv6 with service delivery.
All right. So, hey, thanks guys. So there's been a lot of discussion about SRv6. There's been a lot of discussion about how do we provision it. So far we have seen the cutting edge technology that SRv6 is giving and how it's enabling these 5G networks of the next gen that we are seeing today. So I'm going to touch a bit upon what kind of automation capabilities do we have with Arrcus and ArcOS, and also how we can integrate with well-known tools that are out there in general for you to provision the networks. There's been a lot of discussion about how do we provision and how do we make sure that it flows through the existing workflows. The first thing I want to touch upon is like ArcOS, we tightly integrated with Ansible. So that's kind of an open integration with a well-known DevOps tool that most of us in the networking industry are aware of and how to use it. And the way we kind of build that is underneath, the Ansible, we kind of use ArcAPI modules to kind of interact with these devices in a management plane. So ArcAPI is our homegrown Python-based API module. It can also do multiple northbound APIs like netconf, resconf, or you can just do CLI. So it has full capability when it comes to whatever you do it on CLI, you'll be able to do it on using ArcAPI as well. And the best part about using Ansible in general is, the flexibility in the kind of templates that you get. Like, as a network operator, there are like a bunch of operating systems that are available out there, and you'll have to know the CLI of OS A, OS B. The best part about integrating with Ansible is all you need to know is the concepts of this network or like the general construct that you see in these drafts. As long as you're aware of that, the templates can be generic and it's easier for you to consume because these are all in like YAML format, or like you can template it out and you can reuse parts of that Ansible roles in general to make sure that you have this provisioning being done. Now, the other interesting aspect here is like before you do any sort of provisioning with Ansible, since ArcOS by default enables transactional CLI, transaction-based CLI, you don't have to instantly push the configurations. As soon as you if you want to make a change in the network, all you do is you want to make some changes, you give those changes in the form of your template file, and then you can always validate the configs via Ansible itself because ArcOS supports the transactional CLI based commit based model. Before pushing a config, you can always validate to see if what I'm pushing into the network, is it, does it look correct to me? And only then you can go ahead and push that configuration. And three points that I like to highlight here is in general, like It's quite simple. Like, rather than going to the hoops of having your own provisioning system, like each vendor has their own provisioning system, it's easier to kind of stick to one well-known industry-known tool to kind of provisioning these new layer 3 VPN circuits. Once you have the infrastructure in place, provisioning new circuits is just a press of a button, and then you have these new circuits being provisioned across multiple PEs in the network. And the other important aspect here is like these are all human readable YAML files. Like when you read these files, when you want to configure certain circuits or VPNs across these PEs, you can easily read the file and understand, oh, this is what I'm trying to configure, or this is what I'm trying to do. So that makes it much more easier for anyone in the networking industry to kind of understand what the intent there is in the configuration that you're trying to add to the devices. And as you all know, since Ansible is well known, it's extremely scalable. You can manage your entire network infrastructure with just one single tool by managing the template files that you have. And also not just network infrastructure, as you know, Ansible can be extended and is being used for the compute side as well. So that gives one single platform across all the devices that you want to manage and gives like a single point of interaction with your network in general.
Hey, Aditi, this is Jeremy. So I got to ask, of the customers that are using your product and that have, as somebody said, they were integrating with their existing, automation orchestration platform systems, are they using Ansible? Are these companies that are running your product in production, are they using Ansible to deploy and manage Arrcus in production?
So there are two parts to that question. The first thing is, yes, some of our customers are using Ansible to kind of provision and look at the network in general. And the other part of that question is a lot of these customers have their homegrown tools that they use by default currently. So for those customers, they kind of use ArcAPI underneath to interact with the device, and that kind of seamlessly flows into their workflow. You don't need to have a know-how of something new. It's just seamless in the way it integrates with your existing workflow.
And those that are using Ansible, like could you characterize how big of a deployment they're trying to use? I mean, with Ansible, are they deploying thousands of Arrcus boxes, hundreds of Arrcus boxes? Is it a small number? Just kind of curious.
Sure. So yeah, so far we've seen deployments which are spanning across hundreds of devices using Ansible. So that's a data point for you at this moment.
So they're using Ansible to manage hundreds of Arrcus devices in production.
Correct.
Okay.
Yeah. And yeah, as I was saying, like the seamless integration makes it a popular choice. Like you either have your own existing workflows or you have your own existing APIs. All you need to do is integrate ArcAPI at that point to kind of manage the device. Or if you're using Ansible, all you need to do is have these new roles and the modules being integrated already into your existing system, and then that's about it. You just press a button, and then you'll have these. You have the configs provision on these boxes. So having said that, I actually have a quick demo that I'll walk you through, overviewing all these. And also I'll provision a new circuit in the existing topology that Matt had just demoed, so you guys can see live in action on how it actually happens. So I'll go back to my terminal screen here. So first things first, I have an Ansible playbook here. That's what I'm going to use. And I have 3 hosts that mainly I'm going to use PE1, PE2, and PE3. I'm going to provision a new VRF or a new network instance on all these 3 PEs. And the playbook that I'm going to use here is like Arrcus config PE. The intent of my playbook here is I want to create a loopback interface on all these 3 PE devices and create a new VPN circuit or a new VPN overlay between these 3 PE devices and have that loopback advertised in that PE so that it gets advertised on layer 3 VPN route over SRv6, and then we'll ping those loopbacks at the end. So you guys can see the circuit getting provisioned and also the reachability being established end to end at the end of it. Now, before we do that, I'll also give you guys a quick overview on how this happens. So these, as you can see in the playbook, there are 2 roles that I'm going to leverage here. One is the Arrcus L3 VRF and the layer 3 interfaces roles. I'll probably quickly touch on the Arrcus layer 3 VRF template. So these are standard Gen 2 templates. So it makes reusability of these roles much more simpler. So you can reuse aspects of these and call these roles how you see fit. And these roles are basically defined in mainly machine readable XML format. So Arrcus supports display in multiple formats like XML, JSON, or text. We chose XML because it's much more easier to read and understand what the intent here is, but you can do text-based rules as well. And in this, using the standard Gen 2 templates and the host variables that you see for each of the PEs here. So let's say, for example, on PE1, this is my intent. I want to configure loopback 100 having that IPv4 address and having this IPv6 address. And I want to create a new layer 3 VPN circuit across all 3 PE devices. And I want to name that CEVRF3. I want to redistribute my directly connected routes into V4 and V6. And I also want to have, have to define certain layer 3 VPN constructs like the route distinguisher, route target, and the address families in which you want to export these. So when I'm looking at this file, it's not alien to me. Like, I know these concepts, I know what these mean. So you don't have to have the know-how of the CLI or interacting with the CLI in general. So all this information, it goes back to the template, the Gen 2 template that you see, and it gets pushed onto the devices based on the host vars that you give here. The first things first, let's go back to the box to check to see if there are no CEVRF3, and then we'll provision these new VRFs. Okay, so far on all the 3 PE devices, I just have CEVRF1, VRF2, and similarly on the other one as well, I just have CEVRF1, PE2, and same goes for the other one as well, CEVRF1. Now, we'll go back to the Ansible playbook, kind of do a config validation first. So I'm going to just call my Ansible playbook and call this playbook here and do the config validation. So what this diff check option is going to do is it's going to take those template files, compute all the configuration that it wants to push, send it over to the target machine. It'll ask Arrcus to see, hey, I'm trying to load this configuration file. This is my config diff. Can you tell me what the config diff is? And once Arrcus target machine computes that, it will return back the config diff to you. So from one single station, which is my Arrcus, which is my Ansible server here, I should be able to see what configurations are being pushed on all the 3 PE devices. And if not, so basically, as you can see, these are the config diff that it's pushing. At the end of the playbook, what it's supposed to do is it's going to take these config diffs and it's going to save it to a text file locally so that you can actually see what's there in the text file. And at the end of it, you can see like these are the kind of config diffs that are being pushed for each of these boxes, like, loopback 100 on all 3 devices. They have different IP addresses for each of the PEs. And it's also going to push the layer 3 VPN configs. Okay, so there seems to be some issue with the diff, but let's just probably go and push the configurations to see if it takes effect. Okay, I'm gonna probably abort this. Okay, so what we saw here is that the first thing it did was in the roles that we've defined, it configured the layer 3 interfaces, and then it kind of went and configured the layer 3 VRF here. So let's go back to the device to see if these actually got provisioned or not. And as you can see, there are a couple of commits being performed. That's by the Ansible server that's doing the commits. And we should be able to see a new VRF being provisioned. Earlier, when we saw this output, we just saw CVRF 1 and 2. But as you can see, a new VRF is being provisioned here, which is CVRF 3. Also, let's look at the SIDs to see for these new VRF that's provisioned. Let's look at the running configuration to see what's being pushed. Okay. So whatever was there on the PE1 host vars file, that was the intent that we wanted to configure. We just were able to get the same thing configured on the Arrcus box here. Like, it has the route distinguisher, the route target, what interface you wanted to configure under that particular VRF. And similarly, all this configuration got pushed into all the 3 devices, all the 3 PE devices. And each of them have their own unique RD, but the RT remains same. And then let's quickly check PE3 to see what got pushed here. So yeah, so with a single click of a button, you were able to provision a new VRF across three PE devices. And let's quickly see if the local PE was able to allocate SRv6 sets for this particular new VRF. So when Matt was running the demo, you could just see the sets being allocated for CEVRF1 and 2. But as soon as we provision this new VRF, we can actually see two new sets being provisioned here for CEVRF3. One is for the n.dt4 set, and the other one is the n.dt6 set. And let's also look at the loopback routes that got advertised in L3VPN over SRv6. So I'll just quickly use my alias command here for my ease. And 102.1.101, this is the loopback address on the PE2 device. And similarly, at the same time, we should have also gotten the loopback of PE3 device being advertised in layer 3 VPN. And as you can see, it has all the next stops, which is the SRv6 set. It has all the other attributes, which means at the end of the day, what happened here is like a new VPN circuit got provisioned across all three devices. And also we see the loopbacks being advertised on L3 VPN. So with just a click of a button, we could get a new circuit being provisioned here.
Hey, DT, this is Jeremy again. Can you show me the template, the template that you used with the Ansible for a second?
Yeah. So
not the playbook, but the actual template that generates the configuration that you push.
Here you go.
Right. So you're using Jinja to create XML, but how do I know what the XML is supposed to be to build this template? Like, can I go onto an Arrcus box and dump the config and see it in XML?
Right. Yeah, that's a very good question. So let's say this is we'll probably take a template here, show running config network instance CEVRF1. I just do display XML. And then you get this whole output in here, and then you know exactly what pieces of this output to replace or to integrate it with your existing template.
Got it.
So, yeah. So on an on-demand basis or on need-by-need basis, we usually create these templates for all the customers that are. So we kind of work with the customers to identify what areas of the configs need to be provisioned, and then we work towards generating these templates. So as you can see, the templates that we generate for SRv6 or layer 3 VPN, those come from our existing deployments that we've been seeing so far. So that's how we have the templates in place. Right. So this is the local loopback that is configured, and we do have the loopbacks of PE2 and 3 advertised in layer 3 VPN, and we do have the next stops, which are the SRv6 sets. So all in all, it's quite simple to use the APIs that we provide. Quite simple to use existing well-known tools like Ansible to integrate and provision the network. Scalable in terms of manageability, the limits of Ansible. So it's quite scalable in terms of large-scale production network. Also, it's seamless. Like you have an existing workflow, you can plug this in, and Ansible is a first-class citizen for us. So you can plug it into the existing workflow either by using Ansible or by using the Python Arc API or the netconf, restconf, notebound APIs that we provide. So yeah, that's my demo in short to show you guys how to provision a layer 3 VPN circuit on the existing setup that we are already used for the demo.
This is kind of going back, I think, a little bit to the earlier SRv6 stuff, but didn't have a good chance to ask then, so I'll ask now. So when it comes to SRMPLS and SRv6 and label depth and how big of a stack you can have, what's the longest ERO that you can really do with Arrcus, and what are the limitations there on the Arrcus platform?
Okay. Yeah, Adi, if you remember the specific label depth or SRH size, I don't recall, but there are a couple of aspects there. The first is what's the use case. So if you're creating an ERO for maybe disjoint paths that are manually provisioned, then you could very quickly exceed the stack depth or the SRH size limits. If, on the other hand, you're trying to determine the maximum number of SIDs that are required to achieve, say, TI-LFA coverage in a backbone, there's been a lot of research out there that shows that in most cases, you don't need more than a few, and in many cases, you need only one. So, Adi, do you recall the exact specifications there? I don't know off the top of my head what those limits were.
So the depth, in general, yeah, I don't recall the exact number, but it also kind of depends on the hardware used in certain cases, because that's where the encapsulation is being done. And as Matt has mentioned, there's been a thorough research on the number of SRh headers that you need for each packet, and it's quite handful. It's not much, but yeah.
And
yeah, it's going to be topology as well. Yep.
Okay, and so do you support, binding SIDs and stuff for, joining together some of that stuff?
I believe that's, doing binding SIDs and creating SR policies is something that we have on our sort of near to medium term roadmap. It's something that has, being able to statically configure it is something that we could probably do pretty quickly if you know what the SIDs are and you just want to configure SID 1, SID 2, SID 3. But we're going to want to do it in such a way that it's more usable than that, which means being able to take SR policies that are specified via a connection to a controller, BGP, or even SR policies that are defined in terms of endpoints, colors, and constraints in a policy language like some of the RFC or IETF drafts are showing. The SR policy draft just went to working group last call, so you can read that. That's approaching sort of finality. But yeah, short answer to the question is we don't support binding SID yet in that sense.
And you mentioned PC. I know that Arrcus doesn't have a PC, but you mentioned supporting connectivity to PCs and things like BGP-LS. What about PCEP? Is that supported, or is that coming?
I don't believe we support PCEP now.
Okay,
but it's coming. It's on the roadmap.
Mm-hmm.
I mean, we're going customer use case by use case, and so far for the use cases that actually the demo kind of alluded to, it wasn't required. But that's something that's being added as we speak.
Yeah, we're doing.
The other thing I want to highlight is the SRTE is also another capability the architecture supports, and so essentially that's built in as well. Chris.
Okay. And I got a question from somebody actually here who's not here. What about seamless BFD and inside like of an LSP? Is that supported?
BFD is, yes. KU, do you want to add anything to that?
We do support single hop BFD. For sure.
To summarize, in terms of scalable, seamless, in terms of simple, SRv6 for L3 VPN by virtue of using existing routing protocols that are used for IP, by virtue of requiring no state signaling in the core, and having convergence time on the shoulders of one protocol rather than multiple protocols, and that protocol being fairly optimized. And in terms of it being transparent to IPv6 only nodes and using the great BGP for advertisement of VPN routes. We're using a lot of existing infrastructure, a lot of existing capabilities, as well as making something that's future-proof for an IP infrastructure a la 5G, which really is IP everywhere. And so, again, to this use case of a cell site or edge compute with MSC, you have only to deploy IPv6 into your RAN and selectively deploy SRv6 where it's needed to provide VPN overlay, to provide policy control, TE, and other aspects of your mobile deployment or your edge compute deployment. And a lot of these same capabilities extend into wired access and general internet and network edge. So, with SRv6 on ArcOS with Arrcus, you are getting something that's next gen, but not in such a way that we're reinventing the wheel. We're using a lot of what's good about IP, IPv6, and the existing control planes that are out there.
One quick question, Matt. I know I saw ISIS by itself in the ArcIQ, and you used ISIS for the demo. I was just wondering if we could have done the same thing with OSPF version 3 on ArcOS.
So doing SRv6 and SID with OSPF v3, I don't believe we support yet, but that is roadmap. Yeah, and
yeah, I mean, fundamentally from an architecture point of view, it's seamless. I mean, it's essentially changing a control plane.
Yep.
I mean, it's just that most of the deployments that we've seen for segment routing have been over the ISIS IGP.
Okay, thank you.
But yeah, as you rightly pointed out,
I will point out though that if you have an OSPF v3 core, you can still do SRv6 L3 VPN over that core. That's not a problem at all. You know, it's just a matter of having IPv6 end-to-end connectivity to be able to deploy the solution.
Since we're mentioning various protocols, I'll ask a question that I kind of have about Arrcus in general and with ArcOS. Where's the routing stack come from? Is that something built entirely in-house? Is that FRR? Is it IPI? And well,
I just want to answer something real quick before I answer that. I hope you don't mind. Seamless BFD is supported. I goofed up when I said a single hop BFD. Somebody did ask also about SIDs, and you could do 4 SIDs in one go with Jericho 2, and there is a hardware support actually with some tweaking you could go up to 9 SIDs. Same with the labels. Coming back to your question, and it somewhat dovetails into also the question that Jeremy asked earlier as to why this. And if you step back and take a look at it, one of the things, short answer, we wrote everything from grounds up. And that is because if you look at open architecture, where you want to leverage merchant silicon at scale, the silicon will provide you with non-blocking forwarding fabrics that you can build at different speeds and feeds. But the other thing that you can get with white box at scale is core counts, cheap core counts. On router, on a fixed form factor boxes, you can have 8 cores of Broadwell-based CPU family from Intel. And the thing then is, how do you exploit core counts? Well, the natural answer, people will say, run them as software as processes on Linux like operating system. But you know, in routers, certain processes require far more CPU processing than other processes. And case in point, any protocol that is along the programming path. So we had to do a fully distributed system with non-blocking or minimal blocking architecture, where you have protocols like BGP easily run in parallel in just up to 5 or 6 cores when it's converging. To give you an example on our platform, along the route programming path from routing protocol like BGP down to the point where ASIC gets programmed, or in this case, merchant silicon, we can easily ingest up to 13 to 15 cores. And this required us to fundamentally redesign the software from first principles. And that's how we also support telemetry at scale, because now we can throw the problem at the core counts and the 64-bit memory that is on the box.